Most tutorials focus on the flashy demo. They show one image, one box, one wow moment. But the thing that actually matters is this. Ultralytics is not just one model. It is a workflow layer around a whole family of computer vision tasks, so you can move from a pretrained model to training, validation, prediction, and deployment without building a vision stack from scratch. Think of it like a power drill with interchangeable heads. The drill is the platform, and the head you attach decides whether you are detecting objects, tracking them, segmenting them, classifying them, or estimating pose. That matters because production is never just run the model. It is about choosing the right task, the right model size, and the right deployment path for your accuracy, latency, and maintenance limits. And one common mistake is treating the pretrained demo as production-ready for your own domain. It is a great starting point, not a finished product.
Before you dive in, there's one thing that saves a lot of pain. Make sure your environment matches the tool's floor, not just your machine's mood. Python 3. 8 or newer is required, and PyTorch 1. 8 or newer is the safe baseline. Python is the language you write in, and PyTorch is the deep learning library that actually runs the neural network. If either one is too old, you can waste hours on errors that have nothing to do with your code. The most common mistake here is installing the latest package into an unsupported Python or PyTorch version, then assuming the library is broken. It usually is not. Start with the right versions first, and the rest of the setup gets much smoother. Source, https://github.com/ultralytics/ultralytics. You should also be comfortable with basic Python scripting, which just means you can run a script, import a package, pass arguments, and read a result. You do not need to be a machine learning expert yet, but you should know the basics of computer vision tasks, like classification, which means labeling an image, and detection, which means finding objects and drawing boxes around them. That context matters because different tasks produce different outputs, and if you treat them the same, your code will break in subtle ways. A working CUDA or GPU setup can help a lot, because CUDA is the system that lets NVIDIA GPUs speed up deep learning work, but it is not required to get started. For first experiments, CPU is fine. The real goal here is simple. Get the foundations right now so the actual model work feels easy when you begin.
Most people want to jump straight to predictions, but the real win starts one layer earlier. A clean install. If your Python and PyTorch versions are wrong, nothing else matters because the model may fail before it even loads. The simplest setup is Python 3. 8 or newer with PyTorch 1. 8 or newer, then install Ultralytics into that environment. That gives you the core library and its requirements in one shot, so you can immediately load a model and run inference, which just means getting a prediction from a trained model. Source, https://github.com/ultralytics/ultralytics. The key detail is to run the install in a terminal, not inside Python. That avoids a common mistake where people paste pip commands into the wrong place and think the package is broken. After that, importing YOLO gives you the main entry point for working with Ultralytics models. The example model, YOLO 11N, PT, is a pretrained checkpoint, which means a ready-made set of weights you can load right away. That is perfect for testing the pipeline, because you can confirm the install before writing any real application code. But do not confuse a demo model with a production model for your own domain, because that is where the next trap shows up. Most people rush straight to training, but the fastest way to know your setup is healthy is much simpler. Run a pretrained model on one image and see if it predicts anything sensible. That gives you an end-to-end inference path, which just means the full chain from loading the model to getting results back actually works. It is the best early smoke test because it catches broken installs, bad dependencies, and runtime surprises before you spend hours on custom data. Source, https://github.com/ultralytics/ultralytics. The code is tiny. You import YOLO, which here means a ready-made interface for loading and using the model. Then you load YOLO 11N, PT, where PT is a PyTorch model file, and N means the nano version, a small and fast model that is great for quick checks. Next, you pass in an image URL and get predictions back. That is better than building a manual OpenCV pipeline first, because Ultralytics wraps the common computer vision workflow in one simple API. Source, https://github.com/ultralytics/ultralytics. The important part is not just that it works, but what you do with the output. Results is a structured results object, which means machine-friendly data instead of just pixels drawn on a screen. That matters because production systems need deterministic values like boxes, class ID, masks, or key points, not screenshots. And one common mistake here is assuming this demo model is ready for your custom domain. It is not. Use it to validate the pipeline, then train and test on your own dataset before you ship. But there is a catch most people miss. Most people think the hard part is getting a model to predict. But the real production skill is reading the output correctly. If you cannot inspect the result structure, you are stuck with guesswork, and guesswork breaks pipelines. Ultralytics gives you structured results, which means the model returns data you can program against, not just a pretty image on the screen. That matters because downstream logic usually needs boxes, masks, class ID, or key points, not a screenshot. Source: https://github.com/ultralytics/ultralytics here. Result is a result object, which is just a neatly organized bundle of prediction data. Org shape tells you the original image size. Boxes gives you the detected bounding boxes, which are rectangles around objects. That is much better than trying to parse pixels from a rendered frame, because machine-readable data is stable and easy to filter. You can count objects, ignore low-confidence hits, or trigger alerts without fragile image scraping. A common mistake is assuming every task returns the same kind of output. It does not. Different model heads, meaning the task-specific output layers, produce different result shapes, so you need to match the parser to the task. But there is a catch most people miss. Here's the part most tutorials gloss over. The same workflow can solve different vision problems without forcing you to rewrite your whole pipeline. That matters because real products change. One week you need to know what is in an image. The next week you need to know where each object is. Later, you may need fine-grained outlines or even human pose estimation, which means detecting body key points, the named points on a person's body. Ultralytics supports multiple computer vision tasks, so you can keep one familiar interface while swapping the task to match the job. Source: https://github.com/ultralytics/ultralytics in code. That looks simple on purpose. You load a classification model for one task, then a segmentation model for another. Classification means predicting what the image contains, while segmentation means outlining each object pixel by pixel. The value here is not just convenience. It lowers engineering overhead because your team learns one API and reuses the same patterns as requirements evolve. A common mistake is assuming the demo model is ready for production in every domain. It is not. For real systems, validate on your own data and use the structured results object instead of screen output so your pipeline can work with class ID, masks, boxes, or key points directly. And if this is going into a commercial product, check licensing and deployment guidance early before architecture decisions lock you in. But there is a catch most people miss. A quick inference test is useful, but it is not the finish line. It is more like checking that a car starts before you plan a road trip. The real question is whether the model survives your data, your latency budget, and your deployment setup. Ultralytics frames the full workflow as training, validation, prediction, and deployment, which is the right mental model because each step answers a different production question. Training learns from your data. Validation checks how well it generalizes. Prediction is the real-world use. Deployment is where speed, size, and reliability start to matter just as much as accuracy. Source: https://github.com/ultralytics/ultralytics. That is why the next move is to shift from the pretrained demo to your own dataset plan. A common mistake is treating the default model as production-ready for a custom domain, like factory parts, medical images, or retail shelves. It may look great on sample images, then miss the edge cases that matter in your environment. Planning validation early lets you catch that before shipping. And planning export early helps you avoid the painful surprise that your model is accurate, but too slow or fast, but not robust enough. Use the structured results object, not just what gets drawn on screen, so your pipeline can work with boxes, masks, class ID, or key points in a deterministic way. Source: https://github.com/ultralytics/ultralytics. The code here is the right starting shape, not the final app. You create a YOLO object, which is Ultralytics model wrapper, then point it at a pretrained checkpoint like YOLO 11N. PT. From there, the real work happens on your data with train, val, and export. Training uses your labeled dataset. Validation measures quality on held-out data. Export turns the model into a format like ONGS, which is an interchange format for faster or broader deployment support. That beats trying to weld production logic onto a quick test script, because it keeps your workflow clean and repeatable. One practical warning: if you are building something commercial, check the deployment and enterprise licensing guidance early, before you lock in architecture assumptions. The docs also point to documentation and community support, which becomes valuable the moment your data or runtime gets messy. Source: https://github.com/ultralytics/ultralytics.
Most tutorials stop at the demo image, but that misses the real story. Ultralytics is not just one model. It is a workflow layer around a family of computer vision tasks, which are jobs like finding objects, following them over time, or outlining their shape. Think of it like a power drill with interchangeable heads. Same tool, different job. That matters because production systems do not just need a cool result once. They need the right result, at the right speed with code you can maintain. Under the hood, Ultralytics wraps state-of-the-art YOLO models behind one consistent Python interface, which means one API can route your input to the right task-specific model head. A model head is the part that turns raw features into a specific answer, like boxes, masks, class labels, or key points. Source: https://github.com/ultralytics/ultralytics so detection finds objects. Tracking follows them frame by frame. Instance segmentation outlines each object. Semantic segmentation labels every pixel. Classification assigns a category, and pose estimation predicts body or object key points. Source: https://github.com/ultralytics/ultralytics. The benefit is simple. You do not rewrite your whole pipeline every time the task changes. But there is a catch most people miss.
Ultralytics gives you one consistent Python workflow for going from a quick test to real-world computer vision projects. Quick question: what's the main idea behind Ultralytics? It wraps state-of-the-art YOLO models behind a simple, consistent interface. Quick question: after running a pretrained model, what should you look at first? Check the results object, because it shows predictions, labels, and the structure you'll reuse across tasks. With that foundation, you can move from detection to segmentation, tracking, and beyond with confidence. Ultralytics is best thought of as a practical toolkit for real computer vision work, not just a demo wrapper. It gives you one place to do detection, tracking, segmentation, pose estimation, classification, and more, while keeping the API simple enough that a new developer can get moving fast. The big win is that you can start with a pre-trained model to prove the idea, then move into custom training when your own data demands it. That matters because a warehouse app is never just a warehouse app in the abstract. Your cameras, lighting, angle, and object types will shape the result. So if you are detecting workers, forklifts, and pallets in live feeds, then tracking them frame by frame, Ultralytics gives you a clean path from prototype to production. Source: https://github.com/ultralytics/ultralytics. But there is one mistake that causes a lot of pain: treating the pre-trained demo model like it is already ready for your business. It is not. You need to validate it on your own site, then train on your own dataset before shipping. That is especially true when you want finer detail like segmentation, which means outlining object shapes, or pose estimation, which means finding body key points for safer analytics. Also, make sure your Python and PyTorch versions are supported, because version mismatches can waste hours before you ever reach a model bug. The logical next thing to build after this is a small warehouse pilot with your own